Good morning. My name is Dr. Jayaprakash Nandavedi. I am going to say today about the topic Advanced Digital Signal Processing, and in this, the review of DFT, FFT, IIR, and FIR filters. This is the M.Tech syllabus according to JNTUH. Now, what are we are going to cover in this? The contents are digital signal processing. In this, we are going to cover ADC and sampling, aliasing, discrete time signals, digital filtering, FFT, effects of finite fixed point word length, and moreover to this, efficient DSP application implementation on TMS 320C6X processors. In this, we will see the FIR filter implementation and IR filter implementation. Now, we are going to say that signal processing. In this signal processing, the best examples are human and how this. So, human are the most advanced signal processors. In the terms of speech, pattern recognition, speech synthesis, you can see like how your human brain, human processors works. Suppose 10 days before you saw one person A and today you saw suppose person B. So your brain, and if there is some similarity, some match, then your brain will say, oh, there is some matching in their face, in their height, in their looks and all. So like that way. So your brain do some processing and so like the human processing is like that way. In a speech, some singer process, some few hours before you saw some singers, after that you saw some singers, listen some singers, then your human brain does some that match and tell that. So these are the human processes, and this is the best example of that. So what we are having some difficulty that we are going to, we encounter many types of signals in various applications. Electrical signals, voltage, current, magnetic and electric fields. Electrical signals are there, magnetic field signals are there, acoustic signals are there, some other signals are also there that we will see. So for an example, electrical signals are there. So electrical signals are voltage, current, magnetic and electric fields. Magnetic signals are velocities, force and displacement. Acoustic signals, sound and vibrations. You know, your mobile set having vibrations, and you are familiar with that. Other signals, pressures, temperatures, you know very well. Most real world signals are analog, that you also know that most real world signals are analog, and to process these analog signals, how we convert these analog signals into digital, that we will see in this. So they are continuous in time and amplitude. Convert to voltage or currents using sensors and transducers. You know that one example of sensors. In daily market, you go to the malls and you see that the main entrance of the mall is going to show you that main entrance. You will see that automatic doors are there, that glass doors automatic opens. How that they do? The sensors are there. Sensors. The objects are coming with this speed, and all they give input to the decision system. They say, oh, this some object is coming, then we have to open. Then they open. If object is going away from them, then they close that. That is what they do. Now analog circuits process these signals using resistors, capacitors, inductors and amplifiers, passive elements. So these are the passive resistors, capacitors, inductors. These are the passive elements in electrical signals. Now, analog signal processing examples are, these are very common examples. If you know that FM radio, video processing in traditional TV sets, not nowadays, but traditional TV sets, that video processing used to do analog signal processing, and analog processing during FM radio. Now another topic in this analog signal processing is there are some limitations. And what are those limitations in the terms of accuracy and limited repeatability, more sensitive, prone to electrical noise, inflexibility to changes, means changes to do some changes you will have to be do again and all. So it is complex and it is not easy. Like that, these are the limitations. So in the limitations terms, accuracy limitations are there due to component tolerances, undesired nonlinearity. You know that capacitors, component tolerances. I remember like while doing resistors, there will be for gold 5% tolerances and for silver 10% tolerances and like that. So another limited repeatability due to tolerances. Again there is limitations. Change in environmental conditions, temperature and vibrations. Again temperature, like temperature variations. How this affects these circuits, like summer, if more hot, more temperature is there. Suppose in cold time it will be different. And during sensitivity, limited range of voltage and currents, inflexibility to changes. If you want to do some changes in the circuits, again you have to do from the starting. Difficulty of implementing certain operations, non-linear operations, time varying operations is a difficult, and difficulty in storing information is again one limitation there. So now we are going to see how digital signal processing is and what are the benefits of this. Represent signals by sequence of numbers, sampling or analog to digital conversion. How this analog to digital conversion happens, this we are going to see here by using analog to digital converter device. This converts your analog signal into digital signal, and that is that filtered sample signals that you will see here. Now perform processing on these numbers with a digital processor, digital signal processing. Here we are going to say digital signal processing. That is we are going to see. And reconstruction analog signal from processed numbers. So reconstruct analog signal from processed numbers, like reconstruction of digital to analog converters. That is going to be done using digital to analog converters device. And if we will break this in analog input to analog inputs as an example, so digital recording of music you can see, analog input to digital input, touch tone mobile dialing. So while you know that touch tone mobile dialing, and digital input to analog output, how this is. So text to speech, this is an example of that. Digital input to digital output, compression of a file on a computer. You know that if you have a 200 MB file, then you want to compress and send through mail, then you have to compress WinRAR, WinZip and many other techniques are there. So by compression techniques we used to do. So these are digital input and we are going to get digital output. Digital signal processing. A basic digital signal processing system is composed of basically three things: ADC, DAC and processors. This processor, this is my last slide also we have seen. So this is in more detail like analog to digital converter, providing digital samples of analog input. While we are giving to this system, we are giving analog signal and we are going to get analog digital output. The digital output is sampled out by converting analog signal into digital. Now DAC, converting processed samples to analog output. Digital to analog converter, you can see here in the last. So digital to digital filtered signal we are going to get as an output filtered analog signal. And real-time processing, all processing operation must be complete between two consecutive samples. How this is happening? Like one signal example is given here analog, and how that we are going to get samples. So like that you have taken samples of the signals, and we have processed this digital sample signals to digitally filtered signals by processing through digital processor, and again this has been converted to analog signal as an output. So this is about the digital signal processing. But some pros and cons of digital signal processing are there. Pros. What are the pros and cons? So accuracy can be controlled by choosing word length. Yes, accuracy can be, like we have seen that there is limitations in accuracy. Repeatability, we can repeat repeatable. There is more benefit than this analog signal processing over digital signal processing. Digital signal processing more better in the terms of repeatability. Sensitivity to electrical noise in digital signal processing. Again, dynamic range can be controlled using floating point numbers. Flexibility can be achieved with software implementations. In digital signal processing, we can implement software, and that flexibility more can be implemented. But in analog signal processing, it is not possible. So, and non-linear and time-varying operations are easier to implement. So this also again very important features over analog signal processing. That is what digital signal processing more preferred. Now digital storage is cheap. Again, there was one problem that storage is very difficult there, but here it is easy and cheaper also in terms of cost. Digital information can be encrypted for security. Yes, again, this is very important nowadays. For security terms, digital information can be encrypted. Price, performance, and this digital information encryption is more here public life as well as for the multi-purposes. If you are going to send some, there is security encryption is not required, and that is very important. So there it is again very important thing. Now, price, performance, and reduced time to market. This again this is one important factor of analog signal processing. So this is the benefits of digital signal processing. But again, it is also having some difficulty. This difficulty, sampling causes loss of information. A to D and D to A requires mixed signal hardware. Yes. Some this limited speed of processors. Each processor has limited speed. That is again one limitations. That is the one limitations you can see. That is not yes. We have to compromise. Quantization and round of errors. While after doing sampling, you do quantization. There are also quantization and to quantize and round of errors at the receiver end. That is difficulty in this. But digital signal processing has more benefit over analog signal processing. Again, ADC and samples. And ADC performs following: sampling, quantization, and binary coding. So you know that how that sample we have seen in the last slide, how we do sampling. So for that sampling, for this sample of the signal, we can see that this signal, same signal in a digital form, discrete numbers here, discrete numbers are there in this form. It has been sampled. Now we are going to see sampling rate must be at least twice as much as the highest frequency component of analog input, that fs greater than or equal to 2fm. That is the formula given by Nyquist, and you are aware of that. Aliasing, how that aliasing happens. When sampling rate at fs samples, fs means sampling frequency, samples per second, if k is any positive or negative integer, it is impossible to distinguish between sampled values of sine wave of f naught hertz and a sine wave of f naught plus k fs hertz. So again, aliasing happen how? That suppose this is a signal in this digital form. You can see here this parameters are there. So how this is sampled, like you can see here how this is signal is going to match like this point, and again this point, again here this point, corresponding to this, corresponding to this. So this samples discrete signal, and the frequency is and amplitude here is given in the time form. Now discrete time signals. A continuous signal input is denoted as xt. A discrete time signal is denoted as n. Here difference is, here in discrete we are using n, but continuous we are using t. T stands for time, n stands for number, and n is discrete, where n is equal to 0, 1, 2. 1, 2 like that with numbers. So at a discrete form, discrete terms, some numbers they are going to say. Therefore, discrete time signal is just a collection of samples obtained at regular interval. Sampling frequency, fs greater than or equal to 2fn. That is the sampling frequency, and aliasing. If less than fs less than 2fn, then aliasing happens. Means we are not going to get exact signals what we cannot check. So for that we are going to use that Nyquist criteria. So this is 3 terms. fs equal to, that is the minimum, to fm. That fm is necessary, fs is the sampling frequency. Now common digital sequence. So these are unit step sequence. How this is, here we are saying digital sequences means, of course the term digital included means here we are going to say the terms of n. Here we are not going to use the terms of t. Why? This is not a continuous, this is discrete. Yes. So that is what unit step signal we are not saying. We are going to say here unit step sequence. Why we are saying to say? Because of different sequence, different numbers. That is why we are going to say sequence, not as a signal. So common digital sequences are unit step signals and unit impulse signals. So what are the formulas? Un, that unit step function is denoted in un, and when n is greater than this value, greater than 0, greater than or equal to 0, then amplitude is 1, and when n is less than 0, then that value of amplitude is 0. That is unit step function, unit step sequence you can say. And unit impulse sequence is when n it is defined as n is equal to 0, amplitude is infinity, and other than the 0, that amplitude is 0. Delta, this is denoted as delta n. So this is unit impulse. Direct delta function also you need to say, but here this is in terms of sequence. Direct delta function you need to say times. So these are the some common digital sequences. Now we are going to say the Z transform. You have studied already in your previous classes. Discrete value of Laplace transform is Z transform. Laplace transform has to be, and you are very much familiar with that. Now we are going to say discrete equivalent of that. Same as Laplace transform, but in discrete term. Last we have seen here in continuous and discrete, like t and n. So like that way here, so in discrete terms. So the Z transform is going to say. Now Z transform properties is going to give you linear theorem, shift theorem, and not. So what are the linear properties of Z transform? Z ax plus n plus by yn is equal to a z x n plus b z by n. You know that from previous classes the condition of linearity is superposition and homogeneity and superposition. These two conditions are there. If a sequence follows these two, homogeneity and superposition, then that is linear, otherwise not linear. Now shift theorem, how this is z x n minus m minus m term shift from n, so that is what we are going to say here, z x n and z to the power minus n. This is the shift theorem in Z transform property. Again, not Z action is equal to xz, that is representation of xz as in Z transform for a signal x, for a sequence x of n, and Z transform of this is going to say as a capital X Z is Z transform. Now transfer function. Transfer function, what is a transfer function? Transfer function is the ratio of output to the input. Same here, and here means discrete or digital terms. They are also in continuous term, input to the output signal. So Z transform of the output to the Z transform of the input. So here what is the output or what is the input? Here input is xz and the output is yz. So if we are going to give yz to the xz as a ratio, this is going to be a transfer function of a sequence. And we know how we have calculated here in last xz and yz. We can calculate by the sequence xn, yn. We take z transform and we are going to calculate. So it is. I hope it is easy for you to understand, because you already understand. Now pole zero forms. What are the poles and zeros? So in the terms of poles and zero, the terms which comes under comes in the numerator form, these are zeros, and which terms comes denominator are poles. For an example, B naught Z minus Z1 Z minus Z2 digest up to Z2 Z minus Zm. So this is going to say as a one numerator term, and this Z1 is going to say as a 0, just 0 2. So like that way, some one factor, another factor, and these are going to multiply and give as a number of zeros from this. And for the poles, we are going to see from the denominator. This is just a review class for this. So Z minus P1, Z minus P2, and Z minus. That is why I am going fast with it. Now pole zero plot, you know that from last study how that pole and zero is. Imaginary line and real line, real Z and imaginary Z. X pole inside of out in unit circle and outside of unit circle. One circle we have drawn in the x and y axis, that real axis and imaginary axis, and the radius of this is L1. This is called unit circle, and if any pole comes inside this, then the system is stable and unstable. We'll see later, I think, in this slide also. Yes, here system stability we are going to study. So on the basis of poles and zero, we can say that system is stable. Basically, position of poles affect the system stability. Yes, what the terms we have seen in the last slide, that here we have seen in the slide that poles in the denominator, these are going to be the deciding factor for a system to be stable, but zeros are not going to decide the factor of a system to be stable or not. So one example we can see from this is in the imaginary line, one pole you can see here, we denote the pole with a cross and zeros with a point. So like that way here, one pole is there, and equation transfer function of this is z is here. This is one example of this transfer function is z upon z minus here. So this system is going to, and system is like the sequence is yn is equal to xn plus 0.5 yn minus 1. So this is the system, x is equal to del n. So how this is xn plus 0.5 n minus 1. So this is going to be system sequence, and this is going to be a stable system. How this is? Because this is going to say here only pole, and that pole comes under the unit circle. So this is the factor as a pole going to say inside the unit circle. This is stable. Like that way, if your pole comes at the boundary, then system is marginally stable, and if poles goes outside of the of the circle, unit circle, then this system is unstable. Like here you have seen, here again marginally unstable system, and unstable system because the pole is going out of this. Here one condition is two times pole is there, so this is unstable system. In this condition, one pole is there, and that is on the boundary, so this is marginally stable. Like that way, we are going to say stability with by seeing the poles of a sequence. That's a concept. One example is there how the system is described that you have to do, and you see one sequence is there how the transfer function is there, like how we have to say we have x and y1 action, and we have to get this, we have to convert this into z transform z minus 1, and here n y n and z power minus 1. So this is going to be at the bottom, and we will get it in the transfer, and then on the basis of that you can say stable or unstable, and accordingly you can draw that system unit step and impulse response. Now discrete Fourier transform. Discrete Fourier transform DFT, discrete equivalent to continuous Fourier transform. We have, if you remember, you have studied in your previous classes Fourier transform, and there you have studied discrete continuous Fourier transform. Again there continuous time Fourier series and all you have studied, but we are going to talk here about Fourier transform, and here we are going to say about discrete. Last classes, previous classes, you have studied in your M.Tech continuous, but here we are going to study and seeing that discrete Fourier transform. Discrete, you know that if we are introducing next term as an independent variable n, that becomes n means number, some percent. So that becomes discrete. Now mathematical procedure used to determine the harmonic or frequency content of a discrete signal sequence. Yes, you have seen. Or if anyone have doubt, you can ask later on. The fast Fourier transform FFT. Yes, you have studied this also. Fast Fourier transform is not an approximation of DFT. It gives precisely the same result. If this is going to give same result, then why we are going to use this? Name itself is saying fast Fourier transform. In last classes we have studied in the terms of addition and multiplication, some formula is there, and with that we are going to understand that how this is fast and how much, at what rate it is faster than DFT. So FFT is just an algorithm. It is going to say your calculation fast, reduce the complexity. Now filters. So what filters we are going to study today is, in signal processing, the function of a filter is to remove unwanted parts of a signal. Filter is going to remove unwanted parts of a signal, such as a random noise, or to extract useful part of the signal, such as components lying within the certain frequency range. Now the filter is a device which stop the unwanted signals in the terms of signal, in the terms of parts. You know that filter very well. Now these filters are in two categories. Like two categories is, one is analog filter, another one is digital filter. Analog filter are input electrical voltage or current, which is the direct analog of a physical quantity, sensor output. An example, last slides we have studied analog signals, analog signal processing, sensors are there, sensors at the place of sensors are, I say example of your mouth. So that is one. Component, resistor, transistor, capacitors and all kinds, of course. The output, filtered electrical voltage or current. In the terms of current or voltage, we are going to get out. Applications, noise reductions. So where analog filters are going to be used is analog noise reduction, video signal enhancement, graphic equalizers. So these are the applications, like video signal enhancement. There we use. If time permit, I will say about this more. Now for the time being, we are going to see digital filters. What are these in this? Input digitized sample of analog input requires ADC. Last slides we have seen that ADC, DAC and processors are there. So like that way there, and component digital processor PC means personal computer DSP, ASIC and PTA. Now output is filtered sample requires DSC. Applications noise reduction video sample enhancement graphic like this. You have studied those things, so I am going to do it faster. Now classification of filters. I already said in the previous slide like analog and digital. So now we are going to say first digital filter, after that we will see analog filters and other filters. So what are these analog filters? Digital filters are IIR, like today starting topic only I said in the topic, like DFT, FFT and IIR, and FIR digital filters. So these are the IIR means infinite impulse response, FIR means finite impulse response, name itself is clear. So again this is further categorized into bilinear transform, impulse invariant and step invariant and some others. These are infinite impulse responses of digital filters. And for finite impulse responses, mean square error, minimize and maximize maximal error, that min max error we used to say in short, frequency sampling and others. So this I think we have studied, you may have been the bilinear transform, impulse invariant and step invariant. So especially bilinear transform and impulse invariant transform questions are generally more often. So these two are IIR and FIR, infinite impulse response, and FIR, finite impulse response, are the digital filters. Now we'll see that analog filters. So in analog filters, what are these? I think now this is, you are very comfortable with this pass stop filters. You have seen and you have studied high pass filter, low pass filter, band pass filter, band stop filter and all pass filters, notch filters. High pass filter, you can see that how the high pass filter signal is 0, 1, 1, 0. Low pass filter, which allow low frequency signals. High pass filter, which allows high frequency signals. Band pass signals within some range, some signals are allowed. Band stop filters within some range, some frequency range, signals are not allowed. And all pass filters, this is all filters means all signals are allowed to pass. Notch filters, these are at some frequency range, and this very less range means narrow band, like this you can say narrow band range. Yes, we need to say match filter is again part of your analog filter, winner filter, equalizer filter and others. So after winner filter, like like Kalman filter and nowadays particle filter, so many other filters are also there, but here we are going to say only up to this. And from this pass stop filters we are very much aware. Some other filters are there, like differentiation filter, integration filter, Hilbert transform, smoother, edge detection. Some these filters are also there, some useful. These are also useful filters. Now ideal filter frequency response, we'll see. While seeing that practical filter frequency response and ideal, so before practical we should know that how that and how that H omega, that mod H omega is going to say I don't know y axis and omega is an x axis, like as an amplitude 1 for this figure A, and omega c is the cutoff frequency. How that sharp cutoff frequency there. Actually this is ideal, practically this is not possible like that. Some curve is coming like this, so some 3 dB cutoff you might have heard and you have seen in last classes. Just here I'm going to show you some, just shape how that is high frequency allowed. Yeah, this is low pass filter, high pass filter, and band pass filter, and band stop filter. Now realistic versus ideal filter response. Previously you have seen ideal filters. How actually ideal filters should be like this, but practically how it happens, you can see from this that actual filter response in this way. So in this, yes, this omega is in y-axis and h omega is mod hf omega, response of this filter, and 1 plus delta p, 1 plus, this is 1, amplitude is 1.